Okay, hello class. We will move to the next chapter, which is a vapor-liquid equilibrium. Okay, previously we have learned about the thermodynamics of properties in the fluid. So the last part we cover is how to determine the latent heat in the phase system. We apply the Clausius-Clapeyron equation based on the rules of the linear equation in order to determine the latent heat. Okay, in this chapter, we're gonna learn about the vapor liquid equilibrium. Okay, these are the list of the topic that we'll cover today in this part. Okay, first we're gonna learn about the principle of vapor liquid equilibrium. By the end is this on this topic, you will able to understand the two-phase system which in equilibrium and describe the vapor liquid equilibrium qualitatively. And then we will learn about the 2D and 3D diagram, which you should be able to plot this phase diagram such as PSY or TSY and obtain the relevant equilibrium data from these plots. And then last, we will solve the VLE problem by using simple modems such as the Raoult's law, Henry's law, and modified Raoult's law. We will perform the VLE calculation based on the bubble and dew point that I will explain later to you. Okay, these are the overall or summarize of the topic in this part. Okay, we will talk about the nature of equilibrium that you have learned in your previous module, heat thermodynamic and heat transfer, the phase diagram, how can we describe the changes of the composition based on this diagram, and we will solve this VLE problem using the VLE model throughout the VLE calculations such as bulb point, bubble point, bubble pressure, bulb temperature, dew pressure, and dew temperature, and flash point. Okay, VLE is an equilibrium between liquid phase and vapor phase. Okay, in solving the VLE problem, usually we will tend to determine the temperature, pressure, and the composition, whether in liquid or vapor phase. Okay, the phase composition. Okay, for the liquid composition, it denotes by S. And the vapor composition we denote as Y. Okay, the requirement for the equilibrium which both phases, liquid and vapor, gonna have the same temperature and pressure, and the Gibbs energy for each phases is similar. That we know that the delta G will equal to 0, or delta G liquid equal to delta G vapor. So this is example in a closed system. We're gonna have this different composition between the vapor and liquid at constant or given temperature and pressure. So the equilibrium, usually we will discuss it at the macroscopic level, which is a static condition in which no change occur in the macroscopic properties of the system with time. Okay, why we learn VLE? Okay, the importance of VLE because it is paramount in engineering applications such as distillation, environmental modeling, and general process design. Okay, the VLE is we will learn deeper on the microscopic level because in the real there is no such a static phases along the or occupy the phases from the beginning to the latter that occupy that space. That's why we need to learn VLE because we tend to have the mimic on the real situation. Okay, this really is a useful data in determining the separation of liquid mixture, and usually it can be applied in design the distillation column. Okay, example here we have the graph or the diagram temperature versus, okay, this substance is N-hexane. So we have vapor phases at a higher temperature, and for the lower temperature we have a liquid phases. And then the line, green line here is we have a dew point or dew line, and this is a bubble line. So example here, if we have the overall composition about 0.4, if we move, okay, if we move it to the reduce the temperature of the process, the vapor or the composition tends to have a liquid. And then if we increase the temperature, we're gonna have the composition of the hexane tends to become a vapor phase. So if we have, okay, this is if we have temperature versus the composition, that means we have a fixed pressure. So if we have the if we have this pressure versus the composition, that's means we're gonna have a fixed temperature. So opposite from this previous diagram, we at high pressure, we're gonna have a liquid phase, and the lower is the vapor phase. So the green line here is the dew line, and we're gonna have a bubble line. So let's take a look on this. If we have the initial, we have 0.4 for the overall composition. And if we constant or remain constant the pressure, okay, the when we increase the composition, it will tend to have the touch the dew line, or it will, if we increase the pressure, it will have this liquid phases or increasing the phases until it reaches all the composition in a liquid phase. So we explain the diagram here. We have pressure versus composition. Okay, our component is benzene, and we also have temperature versus the component versus the composition, and we have the benzene as well. Okay, let's take a look on the pressure versus composition. We have fixed temperature at 680 degrees Celsius. Okay, you can see here, okay, example at initial, we have the initial states here. We have the composition at 0.5 here. And then if we increase the pressure, okay, along this line until about 0.62 atm, so we can have this, okay, the overall composition is 0.5. But when we refer to the microscopic level, okay, if we this is the called as tie line here, which is we have to represent two composition here. So for the liquid phases, okay, we can drag this line, okay, the liquid phases as B equal to 0.38 at 0.62 atm. And the vapor phases here, we have 0.YB equal to 0.75. Okay, and then this is, we have this bubble point here, or it represents the liquid phase composition. And we have the dew point here, it represents the vapor phase composition. Okay, the P2, okay, this point here known as the saturation pressure for the component 2. Example, in this system, we have two components, benzene and maybe we have benzene and water. Okay, benzene as the first component and water is second component. So for the P2 saturation, that's mean we have S1. So our component 1 is benzene equal to 0. Since S1 plus S2 equal to 1, so we're going to have S2 equal to 1. So at component 2 equal to all the component 2 is occupied in the system. So we're going to have P2 saturation about 0.4. And if we have here, that's mean we have S1 equal to 1. So S2 equal to 0. So our component or occupied that space is benzene. So the saturation pressure for benzene is maybe 1 here. We have 1 is the 1 atm is the saturation pressure for benzene. Okay, the second diagram here, we have temperature versus composition at fixed pressure at 0.5 atm. So we have as increasing temperature, we're gonna have the liquid phases, and if we have higher temperature, we're gonna have a vapor phase here. Okay, for the vapor phase, it represents the dew point or dew line here. And we have a tie line here, and also for the vapor, for the liquid phase, we have a bubble point here. So example, the initiate, we have 0.5 here. So if we have the vapor liquid plus liquid phases here, so to determine what is the composition for vapor and liquid, okay, using this tie line here. Okay, if we drag it to the bubble point, that's mean it will give the composition about maybe as B here, 0.1. So the composition of benzene at a liquid phase at a temperature 80 degrees Celsius, we have 0.1. So we can get the composition of vapor phase, maybe YB at 0.55. So we have YB at 80 degrees Celsius is 0.55. So this is how we can determine the composition at microscopic level. Okay, starting with the liquid. Okay, this is mentioned about the 3D diagram. So what I would like to highlight here, the first bubble appear or at liquid or known as the bubble point. So we can see the first bubble here for the liquid phase. If all the bubble points combine, known as the bubble line or saturated liquid line. So this is our saturated, we have the saturated liquid line here. And then the vapor or the liquid are in the equilibrium, both have connected through tie line. So it has the same temperature or pressure, depend on the type of the diagram, whether we fix temperature or we fix the pressure. Okay, as decreasing the pressure, more liquid will be evaporated until W. Okay, this is I will explain a later for 3D diagram. So the last drop here of the liquid disappear, known as the dew point. So the combination of dew point known as the dew line. Back to here, we have this. Okay, this is our dew line. So the combination of dew point, we can get dew line. So dew point, that's when we have the last drop of the liquid. So example here, if we increase more temperature, we're gonna have this vapor phase. So the last drop of the liquid here before it proceed to the vapor phase, known as the dew point. So here we have the 3D diagram here. We have the pressure versus composition. the composition can be liquid and vapor, and also we have the temperature here. Okay, so the line here, the straight line here is the we have the bubble line. Okay, this is our the dew line here, the combination of the dew point. Okay, let's start with our first here or initial state or at F here. Okay, if we reduce the pressure here, if we reduce the pressure from the this is our liquid phase here, based on the since this is our saturation or the bubble line here, so we have a liquid phase here. Okay, if we reduce the pressure until it reach the dew line here, it will have the first this is our last drop for the liquid phases, and if we further decrease, it will reach the superheated region in vapor phases. So you can see here, okay, we have this line here known as time line. So we may have two composition at a constant time, so first we have at constant pressure, or if we have based on the temperature, we're gonna have at constant temperature. So we can determine our composition here. Example, if we have the overall composition here, so we're gonna have the composition for X here, and this is our composition of Y or vapor. Okay, the C here we can see is the critical line. Or we have, okay, this is our critical line. There is normal vapor liquid phases in this region. Okay, the PX curve. Okay, this is the detail about the nuts diagram here. So the P, we have the PX here, PX1, and also Y1 here. Okay, from this diagram, we can observe the we have the minimum pressure isotrope if we have this curve, and this is shown of this maximum pressure isotrope. Okay, the liquid balls at the composition with a reduced vapor of similar composition. The liquid does not change in composition as it evaporates. So you can see for this diagram here, if we decrease the pressure, there is no more. We cannot separate the composition, and also it known as the isotrope. That's mean the Y1 or the liquid composition tends to have the similar composition to the vapor phase for the minimum pressure. Okay, if we increase the pressure until at certain pressure here at 450 mmHg or mercury, we have this same composition of liquid and vapor. Those the isotrope can be observed, or this pressure known as the maximum isotrope pressure. So if we have the temperature versus the composition, we gonna reach the maximum temperature isotrope. That's mean we have the same composition of vapor and liquid at a given temperature here, maybe about 80 degrees Celsius for this component. So if same goes if we decrease the pressure until it reach the isotrope that having the minimum temperature, isotrope having the similar composition between the liquid and vapor. Okay, in designing the distillation column, we try to avoid the isotrope because the liquid and vapor phase cannot be separate anymore. So we have the XY diagram. So we have two types with at constant pressure and temperature. So we have the azeotrope condition along the diagonal line of y equal to x here. So you can see here, this is the diagonal line here. We have the same composition of a y and x. Okay, the point at which the curve across here, okay, you can see the point here across this, so known as this represent an azeotrope because we have the for that such, okay, this is for the across this as y we have this azeotrope or azeotrope faces observed here. Okay, for the PT diagram, at A and B saturated liquid, here we have the saturated liquid means the saturated vapor here. So at such a point, a saturated liquid of one composition and saturated vapor of another composition have the same temperature and pressure. Example here, so we have the same temperature and pressure. The two phases therefore known as equilibrium. Okay, let's take a break. Okay, because we tend to avoid the azeotrope example in designing the distillation column. Okay, you may suggest how can we avoid the azeotrope, or maybe to avoid the maximum azeotrope for the temperature or maximum azeotrope for the pressure. How can we remove the azeotrope? So you may try to suggest or think on removing the azeotrope phase. Okay, let's continue to proceed with the simple model for our last topic in this part. Okay, the objective of vapor liquid equilibrium problem is to determine whether temperature, pressure, and phase composition that are in equilibrium. So the three types of the calculation for the bubble point calculation, dew point calculation, and flash point calculation. Okay, the simplest model can be used in solving the VLE problem. We have the Raoult's law, or we have the latter, we have the modification of Raoult's law, Henry's law, and determine the K value that have been observed the correlation between the liquid and vapor phases from the piston chart. Okay, for the first model, we have the Raoult's law. Okay, this is the equation or expression that represent the Raoult's law, which is the Raoult's law stated that partial vapor pressure for each component of an ideal mixture of the liquid here is equal to the vapor pressure of the pure component multiplied by its mole fraction in the mixture. So in proceeding with the Raoult's law, there are two assumptions that we should consider. Okay, for the vapor phase, we consider it at ideal gas stated, which the Raoult's law can only be used at lower or to a moderate pressure. And then for the liquid phase here, also consider an ideal solution, which only valid when the species that comprise the system having the chemical similar structure. The molecular species are not too different in size and are the same chemical in nature. Example, isomer for both meta and paraxylene, benzene or N-heptane, ethanol or propanol, benzene or toluene, basically having the almost similar chemical nature. Okay, the Raoult's law, okay, for the liquid phase and mole fraction, or Y for the vapor phase, or the P1 saturation here is the vapor pressure of pure species at T, or the given temperature. So we have this partial pressure here, or we have partial for the each component P1 equal to YIP, or we have based on the Dalton law, or the sum of P1 or for each component of each species, it give us the total pressure in the system. Okay, these are the limitation and the strength for the Raoult's law here. Okay, the limitation of the Raoult's law, because we tend to have the ideal condition, so it only applicable for pressure from the low pressure to the intermediate pressure, and it can be applied if the P1 saturation is known. So we need to having this P1 saturation. That's mean we gonna determine the or the temperature should be given, or because based on the Raoult's law, we have P saturation equal to A plus B equal to C plus Ti. So basically we need to define the temperature. Okay, the strain is valid for any species present in at a mole fraction approaching unity, which with condition that is vapor is ideal. So basically, because we use the ideal for the vapor and liquid. Okay, the calculation of Raoult's law, it can be categorized into four. We have bulk P, that's mean we need to find the P here, find P, and bulk here we have based on the liquid, so the composition of liquid is given. So we have view P, that's mean we need to find P here and the composition of liquid, so this is our liquid here, bulk here, that's mean we have this liquid. So for the dew here, we have the composition of vapor is given. Okay, for the bulk T, that's mean we need to find T, and then we have the composition of liquid, and then we need to find the temperature as well. We have the composition of vapor. So the word bulk P or T or dew T or P implies the parameter to be calculated. Okay, for Anton equation can be used to determine the saturation pressure for each for the desired or respective species, because for each species specified on the pure species, we can determine the saturation pressure by referring to your table B2. We can have the obtain the value of constant A, B, and C. Okay, we start with the Raoult's law here for the bulk point, and also the dew point. So this is the summary that you can apply the Raoult's law, because we know that the total pressure is equal to the summation of the liquid composition for the bubble point calculation, because the liquid composition is given. So for the dew point, since the vapor composition is given, so we can determine the pressure by consider on the summation of the 1 over composition of vapor phase over divided by P1 saturation, because the temperature is given. P1 or P saturation can be determined from the Anton equation. Okay, this is the general equation for the binary system. Okay, in this topic, we will focus more on the binary system only. That means we have two species in our system. Okay, the guideline to calculate the VLE or perform the VLE calculation through Raoult's law. So we need to determine the saturation pressure. So we have two species. Since we have two species, so we name the species based on 1 and 2. And then we, for example, for the bulk P, so we need to find P, and then the S is given. So we can, why we need to determine here is to prevent the liquid from the boiling, and also to lower the boiling point in vacuum distillation because we need to determine the pressure. Okay, to start it, we have the about P calculation here. So we need to find the pressure. So in order for us to find the pressure, so we need to determine the P Anton or P saturation using the Anton equation for both a species. And then because of T is given, we can simplify, determine the pressure. And then finally, you can determine the vapor phase based on this correlation. And then for the due P here, we need to find P, and then the due, that's mean the composition of vapor is given. So we can use the same method as we determine the about P here. Instead of having the composition of liquid, so for this calculation, we have the composition of vapor. So we need to determine the P saturation using the Anton equation because T or temperature is not changed. So this is the overall step here to determine the due P calculation. To find P, and then the composition of vapor is given. So you can get the value of P here. And then finally, we can determine the value of or the composition of in the liquid phase. Okay, for the bulk temperature, since we need to find the temperature here, so we need to perform the assumption. So because we don't have this value of temperature, so we need to determine or rearrange this, and then we can determine the T saturation. But since we have the T saturation, so it give the value of T gas. So the step to determine the bulk T is we have a few more steps here. First, we need to assume the T saturation by using the or rearrange the Anton equation here, and then we consider this is our, and then we proceed to the T gas because we already defined our T saturation. And then after we determine the T gas here, so once the T calculation is equal to the T gas, we may proceed to determine the, by using that temperature to determine the finalize our temperature, and also finally we can determine our composition of the vapor. If the temperature calculated and the gas temperature is not similar, so we need to repeat this step again. So I will explain to you provide the example later. So the last calculation is due temperature. So we need to find the temperature, and we have the given information of vapor composition. So as usual, we need to determine the T saturation. It gives us the value of gas temperature here. So we need to perform the iteration, and then until we find the T gas is similar to the T calculated or calculated temperature. Okay, we start with determine the composition or the saturation of the temperature for each species, and then it gives us the value of T gas. And then after that, we may determine the P saturation here. You may insert this or rearrange until you determine or you can find the value of T calculator. If the value of T calculator and T gas is similar, you can assume that is finalized, or you can finalize your temperature, and finally you can determine your composition in the liquid phase. If not, you need to perform another gas, or you need to start with another gas of the temperature to determine the gas temperature here. Okay, let's take a look on the example. Assuming Raoult's law. So Raoult's law, that means we have ideal liquid and also ideal vapor. And prepare PXY diagram at temperature here. So that means we need to determine the pressure, the Since the temperature is given, T is given here, and then the next problem is to produce the TSY diagram since the pressure is given, P is given. Okay, these are the species. So benzene turns to our first species and alkylbenzene is our second species. So we start with preparing our PSY diagram, having the constant temperature at 90 degrees Celsius. So we have this, because we have the fixed temperature, we can simplify determine our P saturation for both species. And then using that, you can determine our pressure because pressure is equal to S1, P1 saturation. And we have P1 and P2 saturation. So you may start with S1 here. Oh, sorry, you may start with S1 here. So by performing, maybe we start with 0, 0 0.1, or depend on you, or maybe 0 0.2, 0 0.3. So we can state or specify our S1. So if S1 equal to 0, so S2 equal to 1. So S1 equal to, example here, 0 0.2. So our S2 equal to 0 0.8. So you may carry it until S1 equal to 1, S2 equal to 0. So you may use this equation to determine your pressure. So we have the information on the start way. Okay, S1 equal to 0. So we have this is our S1. So that's why we have the 0 here. And then 1 for S2. And this is our P2 saturation from our previous calculation. So, and then after that, you can proceed to the Y1 here. So we have Y1 because we already determined or stated our S1. We have the value of P1 saturation and P here is determined here. So you can insert your value to determine your Y1. So you may proceed it. And then after that, you just plot the graph of S1 here and Y1. So we have S1 and Y1. So this is our S1 and this is our Y1. So, and then this is our pressure. So you may plot this, this a value, and you're gonna have to, okay, since this is a liquid, this is our bubble line, and this is our dew line. Okay, this is our example here okay, this is our first drop, or no, this is our last drop of the liquid for the S1 here. So you can simplify, determine what is the dew point and also the bubble point for each species here based on this diagram. So we can monitor also our pressure to avoid the azeotrope. Okay, same goes to the, how about TSY here? We have a fixed pressure here. So this is our species. So we need to rearrange and determine our T saturation. So we have T saturation species 1 and species 2 here. So we have this, we know the range of temperature from this 404 based on the species 1 and 2 here. And then we may proceed to determine our P1 saturation by inserting the value of T saturation here. So we can get the value of P1 saturation and P2 saturation here. So you can have P1 saturation, P2 saturation, and then you can determine your S1 and S2. And then finally, you can plot the graph here. So to determine the S1, you just rearrange the, okay, we have P equal to S1, P1 saturation plus S2, P2 saturation. So you may rearrange S1, you can get P minus P1 saturation over P2 1 P2 saturation, because we know that S2 equal to 1 minus S1. So you can get the value of Y1 using this equation. Okay, and then finally we can plot our graph. Okay, this is our dew line, and this is our bubble line, or the first drop of the liquid observed here, and this is our last drop of the liquid. So observe can be observed by using from the dew line. Okay, the next model is Henry's law. So the Henry's law, if we refer the application of the Raoult's law to a species, example species I requires P1 saturation at the T application, or the temperature is given, which is not suitable for the species of which the operating temperature is higher than or critical temperature. Okay, hence the Henry's law is applied for the system at lower and intermediate pressure. So the assumption of ideal condition of the vapor liquid is still valid. And then the species is represent a dilute solution, solute in the liquid phase. That means maybe we have the dilute species of 1 here compared to species 2. Okay, the Henry's law stated that the partial pressure of the species in the vapor phase is directly proportional to the liquid phase mole fraction. So we can get the Henry's constant, or denoted by H here. So the YP here is equal to SI HI. So the H usually is given. So based on this, we can determine our H here. Okay, for the binary system that consists of the diluted species in the liquid phase, so we have the diluted species, you can follow or obey the Henry's law. And then for the vapor phase here, we can follow the Raoult's law. So back to here, we have a system at given temperature and pressure. So we have the diluted species 1 compared than the species 2. It's follow the Henry's law. And then for the vapor phase, we may stick for the Raoult's law. So example here. Okay, back to the example. A concentrated binary solution containing mostly species 2. Okay, that's mean we have H2 because it's more concentrated than S1 in an equilibrium with a vapor phase containing both. So vapor, we have vapor containing both species Y1 and 2. Okay, the pressure of this two-phase system is 1 bar and temperature is at 25 degrees Celsius. Determine from the following data good estimate S1 and Y1. So you may refer to your S1 P equal to I. So we have Henry. So you may refer to this and the answer is given. Okay, try to do it by yourself first. Okay. Okay, I hope that you can answer it. Let's compare the solution with yours. So the given information is Henry's constant at 200 bar. We have P2 saturation for the species 2 here. So this is the Henry's equation. We have Y1P equal to H1S1. The species 2, we can follow the Raoult's law here. So to determine the S and also the Y1. So you solving, okay, we have the P here. Okay, you may use this Y. Okay, this is our first species here. So this is our second species. So you may rearrange S1 equal to P1 minus P saturation, P2 saturation over H1 minus P2 saturation. So finally, we can determine our S1 and then our H1 here, our Y1 here. You may use this correlation. Y1 equal to H1 times S1 over P. So finally, we can get the composition of Y1 here. Okay, next model is modify the Raoult's law because there are a limitation for the Raoult's law. Okay, if a second assumption here in either in the Raoult's law or ideal solution is removed, we remove the ideal solution. So the deviation of ideal liquid in the liquid phase is taken into the consideration by inserting the activity coefficient or denotes by gamma here to the original Raoult's law. So the modified Raoult's law here turns to the vapor phase composition times pressure equal to the liquid phase composition times the activity coefficient and times the its saturation pressure, because we remove the ideal condition for the liquid phase here. And then this is for the bubble calculation or bubble point calculation, because the summation of the vapor phase composition is equal to 1. We can get the P here. And if we have dew point calculation, that's mean we need to we need to find the composition of a liquid. So we can have this, or we need to find the composition of liquid. So we know that we can have this correlation or relate to the pressure. Okay, for the modified Raoult's law, same as the Raoult's law, but it introduced the activity coefficient or gamma in our problem, in solving the problem. So we have the bubble point calculation. So the bubble point, that's mean the given composition is a liquid, and we need to find the vapor composition. We know that the summation or the total vapor composition is equal to 1. Finally, we can determine our pressure. So same goes to the dew point calculation. The composition of vapor is given to us. Okay, these are the guidelines to calculate the VLE calculation using the modified Raoult's law. Okay, since for the modified Raoult's law, we introduced the activity coefficient here. So this is how you can determine the activity coefficient or gamma for both species. Okay, example here, we have ln gamma 1 for species 1. It can be determined by exponential D, or gamma 1 can be determined by exponent D. A here times the liquid composition of species 2 square. So A here is the constant that you can determine from the correlation of the based on the with the temperature, based on the temperature. And then we can also use the Anton equation to determine the saturation pressure, because for the pure species, it has own saturation, it has own saturation pressure, or has on the constant value of B, A, and C here. Okay, we first move to the bulk P. So we need to find the P here, and also the given here is the composition in liquid phase. Okay, the main purpose to solve the bulk P here is to determine the pressure, because it requires the pressure in prevent the liquid from the boiling, or when we design the distillation column, and to determine the boiling or the pressure at below once we lower the boiling point in the vacuum distillation. Okay, this is the summary in determining the bulk P calculation. So we need to find the P here, and then the liquid phase is given. So we have to calculate the A here, the and also it gives us the value of activity coefficient of gamma, and then we can determine the P saturation for each species using the Anton equation. And then finally we can determine our P here and also the composition of species in the vapor phase. Okay, for the due P here, okay, for the due P, we need to determine the P and also the given is the composition of vapor phase. So since we have the constant of fixed temperature, we can simplify determine our P saturation at using Anton equation for each species. And then since the liquid composition is not known, so we need to perform the iteration to determine the activity coefficient by having the gas and calculated, comparing the gas and calculated gamma here. So this is the overall step. You have the value of temperature, and then you can find the saturation pressure for both a species. It give you so we need to next to determine our activity coefficient by using this correlation, because you did already define your pressure. So you can determine your gamma here, and then finally you can also determine your composition of this liquid phase here. And then if the calculated gamma here is not similar to the gas, so you need to proceed with the gas, the gamma, the value of gamma here. And then if yes, you can stop your iteration and then consider the value of a P and also the for the liquid phase here that you have calculated earlier. Okay, for the bulk T, that's mean you need to find the temperature, and then the composition in liquid is given. So you may perform, since the temperature is not given, so you need to perform the initial gas. So by rearrange the Anton equation here, and then you can get the gas temperature using this correlation. And then the summary start to determine the if involve the bulk T calculation. So T, we need to find the T, and then the composition of liquid is given. So we start with the determine our T gas by determining our T saturation from the Anton equation. And then after that, with a given the liquid composition, and then you can determine our gamma here based on the long example here. We have A as 2 square. So you can, since the composition in liquid is given, you can simplify determine our gamma here. And then finally, you need to compare between the calculator and gas by inserting the P saturation in the Anton equation, and then to determine your calculated temperature. And then if you find the similar temperature for both calculator and gas, finally you can assume, or you can consider that temperature as your final value, and then you can determine your composition in vapor phase. Okay, for the last calculation is DUT, is you need to find the temperature, and then the composition of vapor phase is given. And then you can start with the initial gas, or you rearrange the Anton equation to determine your T saturation. It gives you T gas here, and then you need to determine your because the X here is not given, so we need to perform the iteration procedure to determine your gamma here. And then this is the overall step. We start with the saturation temperature, and it gives us the gas temperature, and then we need to determine the gamma, or the gamma here by using this correlation. to define your alpha, and then it give you the composition, and then finally you can determine the calculated gamma and calculated and the gas gamma here, comparing both. Okay, this procedure or the duty calculation for the modified Raoult's law is the most difficult calculation, because you have two parameters that should compare between the calculated and guessed value. And if you found the value is similar, you can proceed, or you can end our ending our iteration to determine your temperature and the composition in liquid phase. Okay, in summary, you are able to define the VLE. What is the VLE? And then you can apply the P as Y, and also apply the T as Y diagram in describing the dew point, bubble point, what is the tie line, and isotrope. And then also we have gone through the application of the Raoult's law and Henry's law, as well as the modified Raoult's law. Okay, for the next topic, we will move to the more on the example related to the modified Raoult's law. Okay, to test your understanding, please submit this assignment to me for your attendance proofs by differentiate between the Raoult's law, Henry's, and also the modified Raoult's law. And then proceed with the example 2.1, provide the detailed calculation. So you may refer to this example. Okay, we have this example here. Okay, try to do by your own. I already give all the answer, and then including produce your own diagram based on this data, based on your own calculation. Using this, you may choose any value of S1 to proceed with. Okay, and then I think that's all for this session. Thank you for your attention, and I'll meet you for the next part. Okay, bye.